All right. So we're going to talk about observing Jupiter and Saturn. The three main topics that we'll cover tonight concern viewing of both planets. So talk about equipment, the planet's position in the sky, etc. We'll then go into some detail on Jupiter and Saturn themselves, talk about the planet, how big it is, what it's made of, and go into a little bit about the moons of each planet. So with viewing, let's talk about viewing. So why now? At the end of August, Saturn is going to be in opposition on August 27th. Later on this fall, Jupiter will be in opposition, more specifically on November 3rd. And I'll cover a little bit more about what opposition is here in a slide or two. Saturn is coming up first, and you'll be able to see Saturn during the August time frame down on the horizon just after sunset. And then as the night progresses, Saturn will rise up into the sky and then go back down before dawn and be on the horizon on the other side. Tomorrow night, Saturn will be fairly close to the moon in the constellation of Aquarius, and it's going to be south-southeast again when the evening starts out. So why opposition? So opposition is really the closest approach that planets that are beyond the orbit of Earth around the sun, specifically Mars, Jupiter, Saturn, Uranus, Neptune, planets that are out beyond us will appear to be closest to us when they're in opposition. And so you see on this little map here, we've got a planet, could be Mars, Saturn, or Jupiter, that is in opposition. And if you think about it, we're kind of in a big celestial track meet. Earth has that inside lane, and Mars, Jupiter, and Saturn have those outside lanes. And as we run the track, we're coming up on Saturn or Jupiter, and we will get to a point where we pass them. And when we pass them, that will be when we are closest to that planet, which, for obvious reasons, is most advantageous for viewing. And then when you're in quadrature, that's when the planet will actually be farther away from us. And we'll talk a little bit about the differences in size that we can encounter when that happens. So the phenomena called retrograde is when we're actually passing the planet in question in that big celestial track meet. So this animation that you see down here, this is with Mars, but you can see that as we pass a planet that's farther out than ourselves, the planet itself has an apparent motion that looks like it's going backwards. And during that period of time called retrograde, that's when we are in opposition, or we're close to being at opposition, kind of at both sides of that loop that you see here on the animation. This next slide just shows a kind of a calendar, if you will, for Jupiter. I have circled here in yellow the periods of time at which retrograde occurs. It's not the best picture in the world. It's a little bit small, but you kind of make out the little loop down here, and the dates that are in pink, I believe in pink, represent the period of time at which Jupiter's in retrograde. And you see that up here for 2024 and for 2025. So just kind of give you an idea of when, in the coming years, Jupiter will be in opposition. Here is a similar picture for Saturn. You'll notice that in each of the bubbles that I have here, at least in the first two, there's actually 3 periods of retrograde motion. And I think that's due to the fact that Saturn is farther out So its lap around the track is much longer than what ours is, certainly, and what Jupiter's is. So you're able to encounter more of these oppositions or these retrograde motions during the course of the year. So I talked a little bit about opposition. One of the reasons that opposition is such a great time to go out and view Saturn and Jupiter is because you're going to be in a position where you're closest to the planet, and the apparent size that we see is almost 50% larger than what you would see when the planet was at, say, in quadrature. So you see over here on the left, during April of 2011, Jupiter was not in opposition. It was out in that area on that diagram called quadrature. So it's farther away from us than it is when it's in opposition. And here on the right, when Jupiter is in opposition, you can see the size. So the apparent size is pretty stark, and that's again one of the reasons that viewing in opposition is what you want to do. It's advantageous to do. Okay, we'll talk a little bit about equipment for viewing. You can view, certainly can view Jupiter, maybe to a lesser degree Saturn, with a number of pieces of equipment. I'll just, before I get into the telescopes, talk a little bit about binoculars, because you can use binoculars to see Jupiter and make out the 4 Galilean moons. And with Saturn, you can, on a good night and a steady hand, with a pair of binoculars, actually make out the rings. So even with binoculars, you can do some pretty cool observing. But if you've got a telescope, refractors of a good size diameter are great instruments to use. The Schmidt-Cassegrain telescopes, which are pretty popular, are also very good. Here, you get some great magnification that can take place because you've got a much longer focal length. And having such a large aperture, you're able to collect a lot of light. Dobsonians are probably your best bang for the buck. So, with a Dobsonian, you can get large diameter telescopes. You couple that with a good eyepiece, you can get some really wonderful views of Jupiter and Saturn. This chart is really nice. It kind of shows, one thing I forgot to mention, I apologize. If you have any questions, please feel free to enter those in the chat. And when we get done with the presentation, I'll circle back and answer those. I apologize for not making that announcement earlier. This chart is nice. It shows you how the aperture of your telescope and focal length can make a difference in the size and detail that you see with that you can see of the planet. So you see down here on the bottom, for a given focal length, you're going to have Jupiter show up as a small dot here if you're at 3 inches or a 3-inch diameter size on your telescope. Here you're at 4, 6, 8, 11, 14, and 18. And then down here you see the size of Jupiter as though you're looking through an 18-inch diameter telescope. So, the size of the telescope is really a big determining factor for, how large you can see the object. A website that I would recommend, astronomytools.com. It's free to use, and what you can do is you can go to that website. You can put in the details on your telescope, such as the diameter, the focal length of your eyepiece, and what Astronomy Tools will come back with is a picture of what Jupiter should look like in your field of view of your eyepiece. So it's a handy tool. It can help you understand, hey, what size if for my telescope, what would it make any difference, or would it help me if I put in a Barlow, if I went to a shorter focal length eyepiece, etc. And again, you can look at not only Jupiter but Saturn, really any celestial body out there. So magnification, depends on the aperture of your telescope and your seeing conditions. And I'll talk a little bit about aperture here first. So if you have a telescope that has, and in my particular instance, I have a very small diameter telescope. It's a 2-inch diameter refracting telescope. And it has a focal length of about 355 millimeters. If I use that telescope with just a normal eyepiece, I will see a really small object in my eyepiece. It'll be very crisp and very clear, like you see over here, but it'll be very small. If I put in that train and extender and take the focal length out to, which I can take it out to like 603 millimeter focal length, it will magnify the object. But since the area in which I'm collecting light is still at 2 inches, what the net effect of that is I'm going to spread that light out over a wider area. So I will see a more magnified object, but it will be dimmer and less detailed. And then you can see here as you introduce even more magnification, perhaps with a Barlow or something of that nature, you'll begin to lose that detail. So that's the effect that aperture can have on your viewing. However, seeing conditions are also a big factor as well. So let's talk a little bit about seeing conditions. So, when a planet is high in the sky, that's really when you want to look at this thing, any object really out in the night sky. You look through about 40 times as much atmosphere when an object is just over the horizon as you do when it's overhead. And so at opposition, you have that opportunity to do that, because during the course of the night, Jupiter and Saturn during this opposition time will ride high in the sky, and you can reduce the amount of atmosphere you're looking at. So that's one factor. A temperature inversion is another factor. So here in Houston, we have, and boy, do we have warm overlayers of air with overlaying a cooler layer of air. And because of that, the atmosphere is very stable. And so there is very little exchange of air vertically. And as a result, you're able to get a more consistent and stable view of the planet, in particular this time of year. As we get out into November and we are going to be looking at Jupiter, we'll have cold fronts that come through. You want to avoid going out and looking at Jupiter, after those cold fronts come through, because you'll have a lot of turbulence, and that will distort the views and make the object shimmer most. You won't be able to really settle in and see the details. So you want to wait a night or two after that happens. Although I could go for a cold front tonight. I don't know about you folks, but I'm ready. Another thing to consider when you're viewing both Saturn and Jupiter are using filters in order to bring out various features on each of these planets. Here you see some filters that are red, green, blue, and yellow. I use filters in my astrophotography. I haven't really used filters a lot during visual, but filters can have the advantage of bringing out details. And this chart here is really a nice chart. I went ahead and bracketed Jupiter and Saturn, and using the column on the left hand side, you can make a determination on which color filter will enable you to see which feature on the planet. So you see here in Jupiter, the belts are particularly enhanced when you're using a light yellow or yellow green filter. If you want to look at the the belts in the red spot. A dark blue filter would help you with that. The Cassini division on Saturn, which is the prominent gap between, I think, the A and the B rings. We'll look at that here in a while. That would be helped by a yellow-green filter. So the filters can help you. I don't know if that will be a big help with respect to light pollution, but if you're in a dark area, using these can really bring out some of the features that you want to look at. Moon transits are another one too, because we'll talk a little bit about that when we talk about Jupiter, but you have an opportunity to see moon transits on that planet, and in this particular case, a dark red will help. Oh, and other thing too, aginaastro.com. I've been able to find some really good information on filters from that website. So check it out if you've got any more questions or want to, have a resource in order to tell, what kind of filter you could use. All right, so let's talk about Jupiter. Jupiter is our biggest planet in our solar system. It's about 12 Earth diameters wide, about 317 times the mass of Earth. It's about 484 million miles from the sun, and it circles the sun every 12 years. So again, as we circle the sun every year, it's every 12 years. That's how we're able to pass it in our big celestial track meet. And this picture right here gives you a pretty good idea about our relative size. So, here's Earth down here, and here's Jupiter up there. So it's a massive planet. The neat thing about Jupiter is it's a very dynamic object in the night sky. So, one of the things that you can do is you can make some observations, even over the course of an evening, and you can really see the planet change. In this particular instance, what we can see, or what we can notice from this, is over a 20-minute time period, we can see it visibly rotate. So you see over here the red spot, or the giant red spot in this position, and 20 minutes later, it's moved over here. You can see a moon. In this case, Io has come into view. So I think, the thing about this that's really fascinating is that there's a lot of change, a lot of dynamic characteristics of Jupiter that you can go out and observe, which really is cool. Jupiter's composition is mostly hydrogen and helium. It does have a rock and ice core, but being something that was formed out in the frost belt, it's going to be predominantly gas, hydrogen and helium in this case. We'll talk a little bit about transits and the shadow of transits. Again, another dynamic feature that I think is really cool to observe. This next diagram kind of explains how, from our perspective here on Earth, we're able to see both a transit and a shadow. And so you see down here, we're looking at Jupiter from this perspective. We have the sun shining on Jupiter from this perspective. And here we have Ganymede out here. We could probably, in this situation, see both Ganymede, maybe just barely see Ganymede, but we can certainly see the shadow that's cast from Ganymede onto the surface of Jupiter. In this particular case, we're able to see Io transiting the planet, and at the right angle, we can probably see its shadow as well. Oh, no, I take that back. Excuse me. We can see Io transiting the planet, but if you look at the sun's direction, the shadow is probably being cast off to the side of Jupiter. So that's how we're able to see both the transits and shadows. This first picture here is a nice example of a transit. In this case, it's a transit of Io, and you can see the transit of the moon over here, and you can kind of barely make it out, but here's the shadow from Io that's cast on the surface of the planet. It's taken by our own Andrea Salaveria. Very nice picture. Here's another picture that I think is really unique. In this particular case, we're able to see three shadows from 3 of the 4 Galilean moons. And so not only can you witness one shadow, but you can see 2, you can see 3, and very cool. And again, another great reason to get out there and look. Jupiter has various features that we'll talk a little bit about here. The first that I want to bring to your attention is what they call a belt. And a belt is actually these dark bands that you see here, these horizontal bands. The dark bands are called belts. And the belts actually are areas where material is falling back down to Earth. So think of it maybe as kind of a rain or a snowstorm of some sort. Only the material that's falling back down to the surface is definitely of a different consistency. And then you have here in the wider bands called zones. And here is where material is actually rising from the surface. So think evaporation like we have here on Earth. The regions actually are the areas that are shown here at the North and the South Pole. So instead of poles, they have regions, kind of more of a not a horizontal strip, but rather maybe like a cap. And that's what you're seeing up here. The clouds, these bands are in flux. So this is a really cool looking animation, and we can see both the belts and the zones in motion. As well, you can see the big red spot, giant red spot here on the surface, rotating and moving as well. So again, these are some great things that you can, with the right equipment, you can actually film and make a video of this and witness the planet's atmosphere in motion. Here's another picture that is a little bit more flat in nature, but again, it kind of demonstrates the way these belts and zones move. If you see here, it almost looks like they're moving countercurrent to each other. One's moving to the right, and this belt up here is moving to the left. But again, very interesting stuff. Much like our own atmosphere, you look at satellite images of clouds and the weather on Earth, and you see the same dynamic motion. Additionally, the atmosphere, like our own atmosphere here on Earth, changes. Here in this particular case, we can see where a belt has actually disappeared from view. So here in 2009, you see a distinct belt right here, and then here a year or so later, it has disappeared and has come back. We've got, in addition to the belts and the zones and the regions, we also have these spots. And here's a picture that kind of shows you the Great Red Spot and then Red Junior over here. Kind of look like tornadoes or cyclones. And then in addition, you can also have storms that can collide and merge and change into one big storm. So in this particular case, you can see a distinct distinct spot here, here, and here. A year later, this middle spot has merged with this spot over here, and now you only have 2. And then 2 years later, you have the merger of the spot over here and here becoming BA. So again, another demonstration or indication of how dynamic the atmosphere is on Jupiter. Here's some images from Voyager, or here's an image from Voyager 1. You can see more distinctly kind of the squiggly pattern of the clouds here probably in a belt, and then here are the storm cyclones here and here. Here is another picture that we see from JUNO. more of a bluish and brownish hue to it. And then this last one from Juno called the Pearl Storm. I really like this one. I'm kind of an art aficionado. In particular, I like Impressionist art, and this one really reminds me of Cezanne or Van Gogh. The brush strokes, the texture, the whole thing. Yet we're looking at a living, breathing planet here. Very cool. The winds of Jupiter are really significant. Typical wind speed on the planet is 200 to 400 miles per hour. The red spot actually has a speed of about 400 miles per hour, and at the poles you're up around 900 miles per hour. So that's pretty impressive wind speeds. Jupiter or Saturn is actually has higher wind speeds, and then Uranus has, I think, the highest. So even though these are impressive, they're by no means the king of the hill in our solar system. Jupiter, like planets, probably are necessary to allow Earth-like planets like us to develop life, intelligent life for sure. And the reason for that is that Jupiter, because of its massive size, is able to act like a vacuum cleaner and take away asteroids, meteors, comets that could come and catastrophically disrupt or destroy life on Earth. So Jupiter's really our friend, even though it's a big planet. It acts like a big brother because it really does help protect us. And a dramatic example of this is the comet Shoemaker-Levy back in the 1990s. And before this, this comet was actually pulled into Jupiter's domain, its gravitational field. Before it hit the planet, it was actually broken apart, as you can see in this picture. And then you can see here that the actual scars from those chunks of the comet impacting the surface of the planet. So here's a scar here, and here. And again, it just kind of is a dramatic demonstration of how Jupiter keeps us safe. Okay, so we'll wrap up our discussion of Jupiter with a quick discussion of the 4 Galilean moons, Io, Europa, Ganymede, and Callisto. Again, these are the ones that you can see transit and see cast their shadows on the surface. Jupiter has many, many more moons than this, but these are kind of the 4 key players. And you see here on this chart kind of a comparison between the 4 Galilean moons and our own Earth, our own moon here that orbits Earth. Our moon is no slouch. It's pretty big. It's not the biggest, but it is pretty sizable compared to what you see orbiting around Jupiter. The 3 inner moons, Io, Europa, and Ganymede, have resonant orbits. Now, resonance can be unstable. If you remember back in your college days or your high school days, in science class, they typically show you a picture of the Tacoma Narrows Bridge in Washington State, and that's the bridge that kind of got the wind came in at a resonant frequency that the bridge had due to its structure, and long and the short of it is the bridge basically tore itself apart. So resonance can be very destructive. In this case, resonance is actually constructive. The resonant orbits that you see here of these 3 moons is very stable, and as a result, these moons can maintain their orbit for a very long period of time. So here's Io, and the nickname here is the pizza planet, probably maybe like the pizza moon, and it is the most volcanic body in the solar system. There are several volcanoes that produce plumes of sulfur and sulfur dioxide that climb high into the sky. The driver for the volcanism on this planet is the the tidal friction between Io and Jupiter and Io and the other Galilean moons that are in the neighborhood. That's probably what the driver is for the volcanism on Io. Very interesting planet or moon rather. And you wouldn't, being out that far into the frost belt, my intuition says I wouldn't expect volcanic activity, but the friction is definitely significant. Europa, very colorful looking moon. It is primarily made of silicate rock and has a water ice crust and probably a nickel iron core. It's one of the smoothest surfaces in the solar system, and it is believed that beneath that surface is a large ocean. There may be some material there that would indicate that there's microbial life there, but that is Europa, and it holds some promise in terms of finding microbial life. Ganymede is the third one out. It is composed approximately of equal amounts of silicate rock and water, and it's fully differentiated, i.e. separated with an iron-rich liquid core and an internal ocean as well. So I think there's a crust on the outside with an ocean underneath. And it's believed that the water on Ganymede is more voluminous than what we have here on Earth. And then we'll wrap up with Callisto. Callisto is composed of approximately equal amounts of rock and ice. It has very low density and surface gravity, and the surface of Callisto is one of the oldest and most heavily cratered in the solar system. Its surface is completely covered with impact craters. So that's Callisto. That's one of the fourth moon that's very far out in terms of orbit. All right, so that kind of gives us an idea of Jupiter, kind of some of the cool things to look at, give you a little bit of the details and the scoop on some of the facts and figures around Jupiter. Now let's jump into Saturn, which is one of my favorite planets. It is the second largest planet after Jupiter, and you can see it here in relation to the other planets in our solar system. Of course, the rings are kind of the star of the show with Saturn. Here's another picture that shows Saturn, again, in relation to our own planet and the sun, Uranus and Neptune. And then here's some facts about Saturn. It orbits the sun once every 29 years. It has a day that's about 10 hours, which I think is in the same neighborhood as Jupiter, about 9.5 times as far away from the sun as Earth is, or put another way, it's about 890 million miles away. It has an axial tilt of 27 degrees, which is pretty close to what we have here, being 23.5. Atmosphere here is mostly hydrogen and helium. Yellow color is due to ammonia crystals in the upper atmosphere, and the gravity of Saturn is approximately the same as Earth. And you may ask yourself, well, gee, that's such a huge planet. How can that be? And I think the answer lies in the core. It has a very tiny core of rock and metal, and most of the volume that you see here is gas. And if you run through the calculations, which I'm sure some astrophysicist or astronomer has done, we have a higher let's see. Yeah, they have a higher gravity than what we have, but not by much. We're almost the same. And while I'm here, I'm going to sip. I think the house is cooling down a little bit, so I'm loving that. Thinking about an ice giant, so good topic for tonight. The rings open and close on Saturn, and they do so on about a 28-year cycle. 13 years on the south side and 15 years on the north side is the way these rings open and close. And when we get to a certain orientation, like you see up here, the rings actually, not technically, but in our visibility of the planet, appear to disappear because we're looking at them edge on like we would a galaxy. And so this is the progression here. Here we're looking. I think this would be in the south side of the planet. This picture right here kind of shows you Saturn and the ring orientation. So I've got highlighted down here August 27th of this year. So we'll be able to see the rings, and it looks like we're going to be able to see the rings from the top, or what I would think they're referring to as the north side. And then here in a couple of years, we'll get to a point where we're looking edge on to the rings, and then we'll begin to look underneath or in the south side of the rings. The rings are really impressive in terms of their overall diameter. And so this is a good picture. It kind of gives you an idea that, from end to end, these rings really span a distance that is the same as from Earth to our moon, which is about 250,000 miles. So they're very large diameter and large surface area. Here is a picture similar to what we saw earlier with Saturn. Here we have zones and belts as well. Instead of referring to the North and South Pole as regions, they call them hoods. Not sure why, but they make that distinction here. And then also what you see out here are the Cassini division and the ENCKE division on these rings. And I've got this next slide, or the slide coming up has we'll show that in a little bit more detail. Much of what we know about Saturn has come from the Cassini mission. This first got into Saturn's neighborhood in 2004, and then in 2017, actually crashed the probe down into Saturn itself, and I think they were doing that in order to take measurements on the atmosphere, etc. But the lion's share of the information we have on Saturn is from Cassini. Again, the rings are really the cool thing about Saturn. I remember when my son was in Cub Scouts, we went to one of the meetings at night, and one of the guys had out his Dobbs telescope, and we looked through that and saw the rings, and that stuck with me ever since. So it was really a gorgeous view. A little bit about the rings. They're mostly ice and water and have a trace amount of rock that varies in size from grains to large boulders. The average thickness of the rings is about 1,000 meters or 1 kilometer. But I think in certain areas that thickness can actually get down to in somewhere in the neighborhood of maybe 15 or 20 meters. So they do vary in thickness, but the average thickness is around 1,000 meters. Here's the picture I was talking about earlier. So here are the rings, and you'll notice here that the Cassini division is this division, or this black area right here, and that division is about 4,700 kilometers or 3,000 miles across. The ENCKE gap is shown over here, and it's entirely within the A ring. This is a relatively small gap, about 325 kilometers in width, and the formation of that gap is caused by a shepherd moon called Pan. That moon is traveling in the A ring, and due to its gravity, it's pulling away material and creating that gap that you see there. You can also see shadows on the rings of Saturn. Of course, this being from Cassini, it's very, apparent and dramatic. I think if you look back in some of the pictures that I showed earlier, some of the pictures from Andre that were featured earlier in the slide pack, you can actually see the shadow when you're looking at kind of the place where the rings go back behind the main body of the planet. So you can probably make those out, but certainly not to this degree. Saturn also has spokes, and I did not know this until I was researching for this presentation. They are seasonal, and they appear at the equinoxes for the equinox dates for Saturn, not Earth. Causes are believed to be either from magnetic instability or meteoroid impacts, but there are distinctive looks like shadows that actually appear on the rings, and these are referred to as spokes, and these occur again at the equinoxes. Here's a storm. So like we saw on Jupiter with the Great Red Spot, storms actually appear and can be observed on Saturn if you got a big enough telescope. And then the North Pole anyway has a very odd feature. There is a hexagonal shape to this the polar region here, and this is thought to be due to a standing wave from varying wind speeds. So very unusual to see that. I know you can see standing waves when you and I've never done this, but you know, when you look at a jet engine, you can see kind of it almost looks like little rings that are coming out of the exhaust. And I think that's the same kind of phenomena that we're seeing here, only on a much larger scale, obviously. We'll talk a little bit about the moons of Saturn. There's some really cool moons. Saturn has a lot of moons. These are kind of some of the majors. Here's the chart that we looked at earlier. I'm going to focus in on Mimas, Enceladus, Titan, and Iaptus. And I hope I'm pronouncing those right. But those are kind of the interesting ones that I saw from the major moons of Saturn. Saturn has at least 83 moons, 53 of these named. So it has a lot of moons out there. So let's talk about some of the cool looking, interesting moons that we see on Saturn. So here's Titan. It's the biggest moon, actually the second largest moon in the solar system after Ganymede. It is the biggest moon in Saturn's orbit. It has an atmosphere of about 95% nitrogen and has a nice yellow hue to it here. And it's big and it's cool to look at, but these next two are really interesting. Mimas is a giant, has a giant crater from a very energetic impact. And from what I read about Mimas, this impact was so energetic it almost split the moon up. I don't know if it split it in half, but it was so impactful that it could have cracked that thing apart. It's a very cool looking object, very stark crater, a lot of craters, but one big crater right there on the side. Iaptus is really cool as well. You look at this, looks like somebody threw a paintball at this thing, or a charcoal briquette that was very, kind of had the consistency of pumice. And it had to have been, I'm surmising, had to have been light material, relatively light material, because it hit the side of the moon, but it didn't really leave any substantial impact crater and just kind of sprayed across the side. And so you have this really neat contrast of this dark coal side over here to the right, and then bright ice on the other side. So and again, in reading up on this moon, its original dark matter is believed to have come from outside of Iaptus. So there wasn't a volcano or anything of that nature that caused that, but rather an impact that was separate from the moon. It's a very, very interesting look. And then we'll talk about Enceladus, and it has a water ice, water vapor set of geysers in a vast under ice ocean. It has organic compounds, and one of the hopes is that there's microbial life here. This is from, I think it's from Cassini. I'm pretty sure it is. But you can see here that you can see on the profile of the moon, you can see these water vapors coming out. Again, the tidal friction between this moon, it's sibling moons, and Saturn is probably responsible for driving these geysers. And then I'm assuming that they were able to tell that this was some kind of a organic compound, because I'm assuming Cassini had spectroscopy equipment and were able to fly by and actually analyze the geysers with the spectrometers in the device. But that's a very dramatic view of geysers coming off of a moon orbiting Saturn. This last picture here is really cool. This is a Saturn eclipse. And so what you have here, we're standing at the viewpoint of Cassini. You've got Saturn out in front and then the moon behind. And it really is neat. You see how those rings are lit up and the shadows from the main body of the planet. So it's really cool looking. Here is a list of places you can get more information on Saturn. And it is the Association of Lunar Planetary Observers is one spot, Sky and Telescope, Wikipedia, Astronomy Magazine, and Space.com. So with that, get out there and do observing this later this month and this fall of Jupiter and Saturn. It's the next best thing to being there. Before I go to the chat, let me just make sure that everybody is aware that tomorrow night we have a presentation from Bill Spizzeri that deals with the cosmic creation of elements, and that will be starting at 7 o'clock. So if your calendar permits, please do join for that. That ought to be really interesting. And so with that, let me go to the chat. And just bear with me a second. See, Don Anderson says, oh, it's a direct message to me. Let me just read it here.
It's just, Chris, it's just another website, University of Nebraska. It really would be cool for outreach with like high school students, because there's a lot of stimulations. When you look at it, it's just endless.
Oh, okay. I mean,
it's
excellent.
Just endless. They use it even in it's for intro astronomy classes, like at the college level, not necessarily the university classes.
Okay.
So like a freshman or a sophomore class, they would use it for that. But it's a great website. You can interact with it. It has labs and it has little quizzes.
Well, great. So everybody get that. It's the University of Nebraska. And I'm assuming that if you go to the University of Nebraska website, you could probably find their astronomy department and get to this.
Yeah.
It's called, the link here is astro.unl.edu. So.
Yeah. There's just, it's endless. There's a ton of fun things to look at. Great for outreach.
Excellent. Thank you.
Uh-huh.
All right. Dan Roy, let's see. Did you have a question, Dan, or was this just a comment?
Oops. Okay, I find you unmute. No, it was just a comment. It was just a comment that Callisto is probably the only place where we'll be able to put a base, because everything else at Jup is just worse than nuclear war.
Okay, so Callisto is probably where we'll put a base of some sort due to the radiation limits everywhere else.
Yep.
Okay, and then you also have a YouTube link that shows the descent of Cassini into Titan.
Yes, this was absolutely fascinating. I had a brief stint on Cassini to help them select their ADA compiler for 1758. And when I saw the result, it is just unbelievable. Those things, it's not water, of course, okay? It's at minus 180 Celsius. You're talking liquid methanes and liquid everything, but it's so striking to see mountains, to see rivers, to see lakes and seas, and even dunes. So we are not done with Titan. This is an extremely interesting system. The pressure on the ground is 1.4 atmosphere. However, the temperature is so low. So the point is this: you will not have to have the same kind of scaphandre that our astronauts are wearing with VA, because the atmospheric pressure is okay, 1.4 atmosphere. Fascinating world.
Excellent. All right. That's all I have in the chat. Does anybody else have any questions? And if they do, they can come off mute and ask. And that's going to go once. That's going to go twice. And that is it. Excellent. Well, listen, again, I thank you for everybody dialing in tonight. And putting up with my dark screen. I did turn the light on because things are cooling down. Yay. And again, tomorrow night, please tune in to see The Cosmic Creation of Elements by Bill Spizzirri. Promises to be really interesting stuff. And with that, I wish you all a pleasant evening and a cool evening.